right, we'll get started here. Questions?
Fourth is not being graded like weighted as part of the test.
Questions?
When are we getting test number 1 back?
Tomorrow.
Did we finish chapter 16 already?
No. We're finishing today. We're starting chapter 17 soon.
Or no.
Thursday.
Wait.
Yeah, there's a holiday, isn't there?
Yeah.
Is Monday a holiday?
Yeah.
Get it back?
So we're missing. We're going to lose one day.
That one.
Other questions?
We got our quizzes back to the first one?
No, the first one I'm going to give you back tomorrow. You're going to do it in class. Oh, quiz? You mean the nomenclature one?
Yeah, the first one.
Yeah, tomorrow. The reactions quiz number 2, you're going to get it back tomorrow, and you're going to have to redo it in class.
Okay, so we can see what we did wrong, right?
Yes.
There we go. Awesome.
Well, I'm not going to tell you what the correct answer, but you can see if you got it right or wrong, and then figure out how to fix it.
Wait, so if we saw that we got it right tomorrow, does that mean that we can't do it again? Or
If you got, let's say if you got the full 5 out of 5,
okay.
you can't do it again because you already got it. But to make it fair,
Okay.
I got to see how many people actually got. The reason I'm doing this is because so few people got it right, the whole thing.
But someone did get it right?
Actually, lots of people did, and
What?
not to penalize them, but they're going to get it a little bonus. But we'll see.
Find the people who got it right.
It's a tricky question. Well, this is a open book, open notes kind of thing, so even if it's tricky, you should be able to work through it or try to work through it. Okay, other questions? No?
When would our chapter 17 test be? So would it be next week from today, right? If we're finishing today?
16, yeah. 16 should be next week, yeah. Although I did get a request about the homework. The homework is 60-something questions long. So
Yeah.
I'll look at that again.
So can we decrease it by half?
Yeah, prop it open. All right, any other questions on the test? I'm just kind of curious because I haven't looked at it yet, but on that last problem, how many people reset that one? Yeah, just curious. You don't have to, but just curious. About that. There are some problems you have to reset. I kept asking yesterday, but what type of problems do you have to reset? What type of problems do you have to reset? Did anybody go back through?
When you're going through like a full base, you're only taking out like a drop. Or you sit on the other side, right?
Well, some problems, like, yesterday's problem is kind of optional. You might reset it, you might not. But there are some problems that if you don't reset it, you aren't going to get the right answer because still it didn't register. If it doesn't register, then you need to get those neurons set. What I said, and if you go back and look, what I said is because of calculator error. That's the one you have to reset because what does your calculator do? It rounds it. So because of calculator round-off error, you got to reset. And so, for example, let's say you start off with 0.25 and x is minus 0.25, then calculator round-off error. And you must reset because the change is too big. You know, if the change is 0.249999999 and your calculator can only carry this many digits, it's going to automatically round it to 100% change rather than a point of whatever it is. And so that's where you have to reset. And so on the practice exam, I put 1 that you have to reset, right? Otherwise, you aren't going to get the right answer. Well, anyway, let's go on and finish that. Did we finish phosphate? What step were we working on? Sodium phosphate.
Step 4.
Step 4, which is water.
It was the final step, yeah.
The final step. Did we complete that calculation, or we didn't?
We didn't start.
We didn't start. All right. Let's go to step 4. And so in a base solution, we're looking always for all the hydroxide ion contributors. And water would be a hydroxide ion contributor. Even though we don't call it Kb, this is a Kb equation because it's a base plus water. But Kw special is both a Ka equation, because it's acid plus water, and it's a Kb equation, it's base plus water, because water is amphoteric. And so this is Kw. The Kw is going to produce some more hydroxide. Will it produce a significant quantity of hydroxide? Probably not. And so we have 0 molar hydronium. How much hydroxide did we end up here with? I think it was 0.0383 ... molar. This is from step 3. Then we're going to get a little bit more hydroxide. Okay, complete this statement then. I don't expect very much additional hydroxide because Kw is small. That's true. But even with a small Kw, I wouldn't even expect.
We have a concentration of hydroxide already.
Right, because we have a concentration. Kw is small, plus we have a concentration of hydroxide, which means
Go to the left.
it can't go to the left. It can't go to the left because this is 0, so we can't go to the left. It has to go to the right. But because we have a large hydroxide, what does that do? Kw is small and we have a large hydroxide.
Less hydroxide, more product formation. It prevents more product formation.
Yeah, which is going to prevent, if both of these were 0, I'd get a lot more product. But since I have a lot of hydroxide here to begin with, I cannot build much product up. And so I expect the change to be even smaller than what is based on K. K, I'm already expecting a small change. Now I expect a very, very small change because of the hydroxide. And so how would you explain that? Since we have hydroxide there to begin with, we don't expect much change.
Wouldn't the hydroxide attack any hydronium that?
Okay, the hydroxide would attack the hydronium immediately and prevent the population of hydronium from increasing much. We actually have a name. If you don't like this predator-prey analogy, the name for this is called, well, I called it, that's one way of thinking about this predator-prey. Another way is thinking about Le Chatelier's principle. Although it can't shift left, it prevents the product from growing very big, having a lot of product here to begin with. But the actual name for this is called the common ion effect. It's because of the common ion effect, I don't expect X to be very big. But the common ion effect, does that register? Do you see a story behind the common ion effect? How would you describe the common ion effect? And so those are the things you want to think about, how the common ion effect is structured. Common ion effect is a common calculation that we do in chapter 17. So here we start to see it in chapter 16. But anyway, I expect X to be very small. The only reason I do step 4 is not to figure out how much additional hydroxide I'm going to get, because how much additional hydroxide will I get? Only negligible. The only reason I'm doing step 4 is to figure out how much hydronium I get, because the amount of hydronium I get will be significant. And so let's go ahead and do that. It'll be the hydronium times the hydroxide, so it's going to be X times 0.0383 plus X. You know, there are a lot of extra digits here. I don't want to really carry. Will the simplifying assumption work? Yes, I'd expect it to work great because I have a combination of small k and common ion effect, or however you want to explain it. And so I expect it to, work wonderfully in this particular problem. We'll see. X comes out to what?
It's 2.6 times 10 to the negative 13.
2.6, give me one more digit. Times 10 to the negative 13. Yeah, that looks like it worked really well. Percent change would be something like the change, which is 10 to the minus 13 over the original, which is about 10 to the minus 2. The percent change is roughly times 10 squared. It would be 10 to the minus 13% change. Is that good? Yeah, it's really good. So that should work. But let's just double check the answer. 2.61 times 10 to the minus 13 molar for hydronium. And the hydroxide will be 0.0383 plus 0.12 zeros. Is 12 zeros going to have an impact on the? No. So it'll be about 0.033. Okay, so can somebody double check these to make sure they multiply out? Oh, it's going to multiply out. It multiplies out, so K is good. Check. All right. Now, are there any other hydroxide contributors? No, this is it. Once we hit the final hydroxide contributor is base solution. And so what we're going to do is we're going to go back through steps 1, step 2, etc., and figure out what is in solution here. If I have a beaker that's labeled 0.100 molar sodium phosphate, what are the species and what is their concentration, starting with the most abundant species? And so what's the most abundant species in solution here? Sodium ion. The sodium ions are going to be the most concentrated at 0.300 molar. Okay, what's the next most concentrated species? PO4. PO4 3 minus, and the concentration? It's not 0.1. This is a PO4 3 minus concentration. .0617 molar. Where did I get that number from? I started with 0.1. Go back to step 1. I started with 0.1, right? But it didn't stay 0.1. It dropped down to, yeah, I had 38.3% hydrolysis. Does everybody see that? And so phosphate stops at the bottom of step 1. It doesn't, does phosphate continue to step 2? Do I lose any more? No. And so that's it for phosphate. What's the next most abundant species? Go back through all the steps and tell me the next most abundant species and what its concentration is. Hydrogen phosphate is not the next most abundant species. Hydroxide is. What's the concentration of hydroxide? 0.0. Okay, then what? Then hydrogen phosphate, which was
0.038.
I'm going to go to 2.9 because it's so close to 3. These aren't the same. Hydroxide slightly above 383. Hydrogen phosphate, monohydrogen phosphate slightly below 383. It's 299.9. Okay, then what? H2, PO4, H2PO4 minus comes out to what?
1.58 times 10 to the negative 7.
Good. Then what? Hydronium? And hydronium is 2.61 times 10 to the minus 13 molar. Okay.
H3PO4.
H3PO4. H3PO4 will be the least abundant at
5.77 times 10 to the negative 18.
times 10 to the negative 18. And so we expect very little phosphoric acid in there, which you'd expect. I mean, this is sodium phosphate, a base, not phosphoric acid. And so these are the species that we find in a beaker that's labeled 0.100 molar sodium phosphate and their concentration. There's a lot of stuff in this solution. All right, let's do another calculation here. We're going to do this. What if we had a beaker that was labeled 0.100 molar H3PO4? Now, are we going to expect the same species? No. I mean, this is sodium phosphate, this is phosphoric acid. Sodium phosphate's a base, phosphoric acid is an acid. So it's going to be different. And so why don't you go ahead and try to work through this particular problem. Here, let me give you some values, because if this is an acid, what do we look for? We look for all the K, what? Ka's, right? We look for all the acid contributors. So we need Ka1, this is a triprotic acid, Ka2, Ka3 for losing the 3 hydrogens, and the last one, Kw. In this order? Maybe, maybe not. You know, it depends on how big the K values are, because usually we start with the biggest hydronium contributor and work our way to the smallest. And what can happen sometimes is that Kw, you know, Ka3 is so weak an acid, sometimes it happens that Kw actually comes before Ka3. And so it's a little unusual, because you'd like to go 1, 2, 3, and then W, but sometimes you have to go 1, 2, Kw, and then Ka3, because Ka3 is smaller than 10 to the minus 14. It's like 10 to the minus 15. If it's 10 to the minus 15, then it's going to be a smaller contributor of hydronium than Kw, and we should rank it from biggest to the smallest. And so what are the Kas? Well, let's not use the one on the chart over here. If we look at these, Ka1 for H3PO4 is equal to Ka for H3PO4, which is equal to, does somebody have their book? No?
Yeah.
I just want to use the values from our book rather than... In the middle of chapter 16, phosphoric acid, there's a table with the Ka1, Ka2, and Ka3 values.
Oh, okay, what are we looking for? Ka1 H3PO4. Ka1 is 7.1 times 10 to the negative 3.
Okay, thank you. What is Ka2? Ka2 of H3PO4 is just a Ka for H2PO4 minus. It's a triprotic acid, so losing the second proton, Ka2 would be
6.3 times 10 to the negative 8.
and then finally Ka3 for phosphoric acid, which would be equal to Ka for monohydrogen phosphate, losing that last proton, is?
That would be 4.2 times 10 to the negative 13.
Good thing. Then Kw, which we know is 1.0 times 10 to the minus 14. And so is this the order we do it? Which one's going to be the biggest hydronium ion contributor? K1, then K2, then
K3.
and then Kw. And so we would do it in this order because we're going from biggest to smallest. Sometimes we have to rearrange the order depending on where Kw fits. So why don't you go ahead and get started. If you had a beaker that's labeled 0.100 molar phosphoric acid, what species are we going to find? Actually, and in what concentrations? Now, you would do all these steps if I asked you what species, what the solution inventory is. But would you do all these steps if I only asked you what the pH is? If I asked you what the pH is, then you know what? I wouldn't bother with Ka2, Ka3, or Kw. Why? Because when you look at this, most of the hydronium is going to be produced in step 1. This is the biggest producer. Then when you look at step 2, it's 5 orders of magnitude smaller. Do you think step 2 is going to contribute? It's insignificant. It's just like back over here when we're looking at the hydroxide, most of the hydroxide was produced in step 1. In fact, in step 1, how much hydroxide did we produce? 0.0383. Then we added a minuscule amount in step 2. Remember, we didn't add that much additional. This was 0.00, 6 zeros, or 1.5. And so if we were interested in the pH of this, I wouldn't have bothered with step 2 on. I would have just done step 1, you know, because from step 1 I could get the hydroxide. From the hydroxide I could get the POH. And from the POH I could get the pH. I didn't have to go all the way to step 4 to get my hydronium to get the pH, because you know what? These two numbers are going to come out the same. They should come out the same because the hydroxide and hydronium are related by kW or pKW. And so I could have saved a lot of time here if I'm only interested in pH. And so in a lot of the chapter 16 questions, they're only interested in the pH. If you're only interested in the pH and you have a polyprotic, then just do step 1. Because that's where most of the... But you have to look at the numbers here. Because what if this were not 10 to the minus 8? What if this were 10 to the minus 4? If this were 10 to the minus 3, this is 10 to the minus 3, this is 10 to the minus 4, would step 2 maybe contribute a more significant amount? Yes. And then I'd worry about step 2. In your homework, what you're going to see is a case. The classic example of where we have to worry about step 2 is for sulfuric acid. Let me point this up here. Sulfuric acid is a diprotic acid. And so if you look at sulfuric acid, most of the hydronium is produced in step 1. But step 2, here, HSO4 minus, losing another proton. For sulfuric acid, because step 2 has a fairly big K, this K is 0.012. And so 0.012 is considered big. Then when we have a fairly big K like 0.012, it contributes a significant quantity of extra hydronium. And so for something like the pH of sulfuric acid, you have to do step 1 and step 2. Otherwise, you're going to be missing about 11% of the total hydronium. About 11% is produced in step 2. Would you worry about kW? You know, so you're going from a K of 0.012 to a K of 10 to the minus 14. Would you worry about kW? No. You wouldn't. And so we look at the numbers here and see, you know, if the question were what is the pH of this, step 1's enough. If the question is what's the inventory of this, then I got to do 4 steps. These are all the hydronium ion producers. What about all the KBs? You know, this is amphoteric, this is amphoteric, this is amphoteric. Do we have to do the KBs? No, because the KBs would be excessive. We wouldn't call it excessive. We'd call it another name. Redundant. They would be redundant. So there's no need to do them, right? Well, why don't you get started on this and see how this, you know, it's the same type of setup as we did for the sodium phosphate. Let me stop the recording. I'll start it again.